Okay, so maybe I should start. My name is Ravi Sinha, and this evening I am going to talk to you about the origin of the universe and its subsequent history. Um, we all live in the same universe. We all try to deal with whatever it throws at us. We all read about it occasionally in some popular science magazine or newspaper. Occasionally, we try to recall what we learned in our high school. I am not going to assume anything more than that on your part. So I would try to keep it as simple as I can, and let us see how it goes. So universe obviously is a very large subject, and one of the problems is that we will have to deal with very large numbers, very large distances, very large sizes, so large that it is difficult to um, make an image of the sizes and distances in one's mind. That is not going to be difficult only for you or me. It is difficult also for the frontline scientists. Human mind is such that it can make good pictures of things that it encounters at it more or less at its own sizes, you know and universe is too large compared to us, so that difficulty will be there. So what I will do, in the beginning itself, let me just set some rules. If you hear me saying something like 10 to the power 9, so you should know that I am talking about 1 followed by 9 zeros. 10 to the power 9, 1 followed by 9 zeros, that's a billion. So 10 to the power 3 is 1,000, 10 to the power 6 is a million, 10 to the power 9 is a billion, 10 to the power 12 is a trillion, and so on. Um, the distances are going to be more of a problem. Um, Distances, when talking about universe, we will talk of something called light year. By light year, we will mean the distance that light travels in 1 year. That will be called light year. Now, you know that light travels 300,000 kilometers in a second, so it will cover quite a bit of distance in a year. Actually, uh, if you calculate it after this lecture is over, you can go use your calculator and calculate light year, and you will find that it will be something like close to 10 trillion kilometers. To be more accurate, 9.46 trillion kilometers. So each time talking about 9.46 trillion kilometers, I will just simply say 1 light year. And if you compare the distances, um, moon, which is something like 385,000 kilometers from here, um, light takes 1.28 seconds to reach moon. So for light, it is a 1.3 second drive, more or less. If you talk of sun, our sun, then the mean distance from Earth is 150 million kilometers. And that's for light, it's roughly 8-minute drive. So these are our neighborhoods, sun and moon. These are just plain, you can say that when we are going to talk about universe, we feel like we can touch them. They are 1.28 second away, moon, 8 minutes away, sun. The nearest star, sun is a star. This is our star. A star is something which has its own energy sources. Nuclear reactions go in the core of stars, and they generate energy and they generate light. That is why we can see them long distance. So, so the nearest star to Sun is Proxima Centauri, and that is 4.2 light years. Light will take 4.2 years to reach from Proxima Centauri to us. So first I will just give you an idea about what is there in the universe and what are the sizes, and then we will get into its history, and so on, and how and when and how we came to know things about this universe. So our galaxy is called Milky Way. Galaxies are large collection of stars. Our galaxy is Milky Way, and its diameter, it's a spiral galaxy. So a spiral, for example, in India, you have in Diwali time these spiral crackers that when you light them, they rotate. That that kind of, or in India again you have mosquito coils. Those are like spiral. So the our galaxy Milky Way is a spiral, and its diameter is 120,000 light years. That's the diameter, and its thickness is comparatively small. Thickness is 2,000 light years. So it's a spiral of stars. In that spiral, stars are located at quite a bit of distance from each other. You know that the nearest star, as I said, Proxima Centauri, was 4.2 light years. But compared to the size of the galaxy, the stars are, it is dotted with billions of stars, and these stars are almost in a plane, in the plane of the spiral, and the thickness, is small, that is 2,000 light years. Our sun, our location, is somewhat towards the outer side of the in the outer arms of the spiral, and the distance of the center of the galaxy from our sun or from us is something like 26,000 light years. Total number of stars in our galaxy, in Milky Way, is something like 100 to 400 billions of them. 100 to 400 billions. If you were to weigh the entire Milky Way, the galaxy, its mass will be equal to 900 billion solar masses. Solar mass is mass of the sun. So 900 billion suns, equivalent to that much of mass is total there in our galaxy. And at the center of our galaxy, there is a massive black hole. You know, the black hole itself is more than 4 million solar masses. So that's the, in nutshell, that is where we live. That is the Milky Way. The nearest galaxy to Milky Way is called Andromeda Galaxy. Now, Andromeda Galaxy is 2.5 million light years away from us, from Milky Way, and it is roughly of the same size or mass, as us, 1.25 times the mass of Milky Way. That's the next door galaxy. And we live, these galaxies are often members of clusters and superclusters of galaxy. For example, Milky Way is a member of something called Virgo supercluster. Virgo supercluster, the diameter is 110 million light years. Remember, the nearest galaxy is 2.5 million light years away from us. And the supercluster in which we live, the total size, the diameter of the supercluster is 110 million light years. And it has the luminosity of this supercluster, how much light, if somebody had to observe the light emanating from Virgo supercluster from far away, how much light would that person see? It will be equivalent to um, 30 or 3 no not 30 3 trillion suns, that much luminosity, you know and its mass is um, a thousand trillion solar masses. That is the size of the Virgo superclusters. Of course, superclusters has inside them many clusters and local groups. For example, our local group in which Milky Way is a member, has 36 galaxies. So if you were to, as I said, if you were to go across at the speed of light from one end of Virgo supercluster to the other end, for light, it will take 110 million years. That's the size of a supercluster. Now, next level will be the observable universe itself. The observable means potentially what we can see in the universe, not that all that we see. Light takes billions of years to reach us from far away places, and there are areas of universe, there are parts of universe from which light has not reached us yet, but potentially it can reach us. Of course, there could be parts of universe from which light will never reach us, and we will see why. That has something to do with the expansion of the universe, and we will come to that in a bit. So the observable universe, the universe from which potentially we can receive light, um, that has about 10 million superclusters. Its diameter is, one end from one end to the other end. The total distance is 93 billion light years. Remember, 93 billion light years. Total mass that is there, total mass of ordinary matter. And why I call ordinary matter, it will become clear in a minute, because there are other kinds of matter in the universe. There are other kinds of matter and there are other kinds of energy in the universe. So the ordinary matter in the observable universe is roughly equivalent to 10 to the power 23 solar masses, equivalent to 1 followed by 23 zeros. Another way of saying is that something like 100 billion trillion, that many suns, will, that much mass, will is there, ordinary matter is there in the observable part of the universe. The observable part of the universe has 2 trillion galaxies, and roughly each galaxy, on the average, you can say that has a trillion stars. So in the observable universe, you have roughly a trillion stars of various sizes. Our sun, for example, is a medium-sized star. There are many stars larger than sun, and there are many stars smaller than sun. So um, at the at this this is, I mean, you can ask a question, you can keep in mind this question, that if I'm saying that the diameter of the universe is 93 billion light years, and soon we will learn that universe is uh, only 13.8 billion years old. Why we say that, we will come in a minute. Big Bang happened 13.7 billion, 13.7 or 8 billion years ago. So light has had time to travel at max 13.8 billion years. So you would imagine that the maximum distance that one could have in the universe right now is 13.8 billion light years. And I am saying that the diameter of the observable universe is something like 46 billion light years. That is because universe has been expanding, and you can keep in mind the question that, can the universe expand faster than the speed of light? Because it will need to do that, because otherwise the size of the universe would have been not more than 13.8 billion light years, but the size is much larger than that, and that is because of the expansion. Only one more thing I will say about the universe, size of the universe and what its content is, that at a very large scale, it is it is very uniform, it is homogeneous, and it is isotropic. It is in which no matter which direction you see, it will appear the same. And the density of stars and galaxies in any volume here and in any volume, in any large volume here and in any large volume several million light years away will be the same. So it is almost like, you can say that the gas in your room where you are sitting, you know, in a typical room, you can say the gas molecules, there will be 10 to the power 24 or 25 gas molecules roughly, a rough estimate, in your room. Same way the universe has 10 to the power 24 galaxies. So it's almost like your room, the universe, molecules are like galaxies. There are 10 to the power 24 galaxies in the universe. There are 10 to the power 24 molecules in your air molecules in your room. It's almost like that, with one big difference, that the air molecules in your room are um, violently, clashing with each other, uh, running into each other. Galaxies are not running into each other, not that, that often. Very rarely they will run into each other, but they are just expanding, running away from each other. Their galaxies are running away from each other. So the motion of galaxies in the universe is much more ordered than the air molecules in your room. But as the air molecule in your room is very homogeneous and isotropic, its density is same in every part of the room and in every direction of the room. Same way, on a very large scale, the universe is homogeneous and isotropic. The density of galaxies in large volumes is same all over the universe. Of course, I mean, this is a difficult thing for somebody who comes to know it for the first time, because we are at a very small scale and we see matter very, you know pieces of matter, and very uneven density around us. Even with the telescopes, we see there are stars in there are stars collected in galaxies, clustered in galaxies, galaxies clustered in clusters and superclusters. So it is not homogeneous, but on a very large scale I am talking about, it is homogeneous. So it is clumps are there, clumps of galaxies are there, but overall in the universe it is more uniform. Now let us quickly deal with the composition of the universe. you know and this is something which I am going to state just to keep in mind, and each of those terms will be explained a little later. The ordinary matter of which we are made and what we see, you know, is only 5% of the energy and matter in the universe. All energy and matter that is there in the universe, only 5% of it is the normal form of matter and energy from which we are built, sun, earth, and so on. And actually it is what you see, the visible ordinary matter, the matter that you can see, that emits light, that is in the form of stars and galaxies, that actually is only 1% of the universe. 3.5% are the intergalactic atoms. Intergalactic atoms are very few and far between. In a few cubic meter, 1 meter by 1 meter by 1 meter, that much of intergalactic space, you will have only a few atoms. It is very rare. Whereas in your room, as I said, you have 10 to the power 24 of them. That's the density of air we are accustomed to. But the intergalactic space has a few atoms, but the universe is so large that large part of ordinary matter is in the form of those intergalactic atoms. Only 1% of matter, 1% of mass and energy in the universe is accounted for by the ordinary visible matter. So let us talk about ordinary matter, that is 5%. Then what else is 95%? 25% of the universe is of the content of the universe, energy and matter content of the universe. 25% of it is something called dark matter. We know that it is there, and we will, little later we will know how we know it. We know that it is there, but we don't know what it is. That is dark matter. That is 25% of the universe. And then most of the universe's energy, most of the content of universe is something called dark energy, which is 70% of the universe. Dark energy, we will talk a whole lot more about it. Dark energy is energy in a way contained in the vacuum itself, in the intergalactic space itself. No. Right now it will sound very mysterious to you, but we will talk more about it. So dark energy is 70%. We don't know what it is, but we know that it is there. We will see in a minute that we know definitely it is there. Dark matter, we don't know what it is, but we know that it is definitely there. Its effect we have measured, and that is 25% of the universe. Ordinary matter is only 5%, and the ordinary visible ordinary matter is only 1%. One more thing I need to mention about the universe is that the average temperature of the universe it's very cold. It is at the liquid almost at liquid helium temperature at 2.7 degree Kelvin, which is minus 270 degrees centigrade. 270 degrees centigrade below zero. That is the average temperature of the universe. How do we know it? We know it through the whole universe is filled with something called cosmic microwave background radiation. There is a radiation. Microwave radiation means it's long wavelength radiation. As visible light, it is 4,000 angstrom to 7,000 angstrom. Angstrom is 10 to the power minus 8 centimeters, or meters. Oh, I don't know. 10 to the power minus 8, I think, centimeters, angstrom, so 4,000 angstrom to 7,000 angstrom, that is visible light. This microwave background, the wavelength is much longer. The energy contained in each particle of this radiation is much less, and the whole universe is kind of bathed into, filled with this microwave background radiation, with this very low energy radiation, and the temperature corresponding to that radiation is 2.7 degree Kelvin. That is what is taken as the average temperature of the universe. The other fact I will state without telling you why, how do we know it, I mean we will come to that in a minute, is that universe is expanding. When we say that universe is expanding, what do we mean? We mean that the intergalactic space is stretching. That the distance between one galaxy and another, one cluster and another, of galaxies, that is stretching. It is not that each galaxy is expanding or each solar system is expanding. We will see later that inside a galaxy, the gravitational attraction is dominant, so it overcomes the expansion of a space itself. But if you go far away from matter, from galaxies, then the space itself is expanding. And that space is expanding because that space mysteriously has some energy inside it which has repulsive gravity, which behaves as if its gravity is repulsive. It is pushing itself out. So the universe is expanding doesn't mean that all of us are expanding, doesn't mean that each clump of matter is expanding. The universe is expanding means the intergalactic space is expanding. The size of the universe is expanding, but galaxies are not expanding, because there the gravitational attraction does not let it expand, or it overcomes the expansion that seems to be the nature of empty space. So empty space by itself is expanding, but the expansion rate of empty space is compensated inside a galaxy where there is enough matter for gravitational attraction to dominate, you know, but elsewhere the space itself is expanding. So now we have a collection of questions, and now we will get into this the part that why, how do we know these things. We come to that part, and the questions we have is that how do we know the universe is expanding. you know what is dark energy? Of course we don't know, but we have to ask what is dark energy, and why does the universe need it. you know what is dark matter? Of course the answer we will see is not there yet, but we know that it is there. And how do we know that dark matter is there? you know and where did this cosmic microwave background radiation come from, and what is the overall chemical composition of the universe? These are the large questions when you are dealing with entire universe, and these are the questions that must be answered. And when you try to answer these questions, then you come to a theory or a model of the origin of universe, which is called hot big bang model, or or lambda CDM, which means that a Big Bang model that needs dark energy, that is lambda. Lambda, Einstein's cosmological constant, we will talk in a minute. So it needs lambda, which is dark energy, and cold dark matter. The dark matter is cold. It is not, it is not emitting any energy. We don't see that. And hot big bang because the initial stages in the initial stages of its history, near the time of big bang, overall the universe was very hot. So this is called the standard model of cosmology. So keep those 4 5 questions in mind, and then the first question we are coming to is that how do we know that the universe is expanding? And this is a very fascinating story. The story starts like many stories, most of the stories in fundamental physics in 20th century physics. This story too starts with Einstein. Einstein, um, when he was 25, 26 years old, came up with a special theory of relativity. Special theory of relativity, he came up with trying to reconcile Newtonian mechanics and electrodynamics, electromagnetism. You can say there was a conflict between what Newton was saying and what Maxwell, whose equations describe electrodynamics or electromagnetism. There was a big conflict between what Newton was saying about space, time, and so on, and what Maxwell was saying, indirectly saying. And in order to resolve that contradiction, um, Einstein came up with a special relativity. The main move he made was that he stipulated an ultimate speed limit. Nothing can move faster than the speed of light. So speed of light is the ultimate speed limit. And by postulating this, he reconciled Newton with Maxwell, or rather, he modified Newton in order to obey Maxwell. You know, you can say. I don't have time to go into the details of these things, but the famous formula that came out of a special theory of relativity, that is E is equal to mc square. Matter and energy are convertible into each other, and there is a formula that tells that if you convert matter into energy, you can calculate that, and that's the formula. E is equal to mc square. Huge amount of energy you get when you convert a little bit of matter into energy. That's a difficult thing to do, but in nuclear bombs and in nuclear reactions, that's what you do. You convert matter into energy. But anyway, we have to get somewhere else. Uh, 10 years later, this was a special theory was in 1905, and 10 years later in 1915, Einstein came up with general relativity. And this he came up trying to reconcile special relativity and theory of gravitation. Newtonian theory of gravitation did not obey special relativity. So you had to rework the theory of gravitation because everything must obey special relativity. Everything in nature must obey. There has to be an ultimate speed limit. And in Newtonian theory of gravitation, there was no speed limit. If the gravitational force of sun does not take any time in reaching earth. So if suppose sun were to disappear, according to Newton, the earth will become instantaneously free. The moment sun disappears, I'm just talking of a hypothetical situation, the moment sun disappears, immediately earth will become free of sun's gravitational force. That was Newton's theory. But Einstein's theory said that it will take time. Nothing, no effect can move from one place to another faster than the speed of light. So it will take 8 minutes for earth to become free from gravitational force of earth after the sun has disappeared, because earth will come to know that sun has disappeared only after 8 minutes. So it's a you might say what big deal, but it's a big difference. It's a altogether different kind of theory, general relativity, that Einstein came up with. Again, I don't have time to go into the details of the theory, but let me just give you some metaphors or some images of the theory. That one of the conceptual revolutions of general relativity was that it was at the same time, it was simultaneously a theory of space, time, and gravitation. So what it said was that space-time is not something that is inert in which matter, you know, plays out its drama. Matter runs around, and nothing happens to space-time. It is just empty space. You cannot do anything to empty space. You can just run around in empty space. But general relativity said that no, matter affects empty space. Matter makes empty space curved. So in a way, matter interacts with empty space and empty space interacts with matter. One of the famous sentences in which general relativity was described by a famous physicist, John Wheeler. He used to say that matter tells space how to curve and space tells matter how to move. So this interaction between matter and empty space and time, I will often call space time, because in special relativity has joined them together. Space and time must be talked together. They don't make sense in special relativity and general relativity separately. But again, those details I cannot go into. But you can just imagine that in empty space, you will imagine that if you have 2 points, you can draw a straight line between those 2 points. That is Euclid, geometry that you learn. That 2 points can always be joined with a straight line. But suppose you have a black hole, a very massive object nearby, and you have 2 points there, and you draw the straightest line between those 2 points. If there is a very large mass nearby, something like a black hole or a sun or something, you cannot draw a straight line between those 2 points. Or you can say that if you draw a straight line between those 2 points will be the line itself will be a little bit curved. So if something moves in a straight line in absolutely empty space where there is no gravitation, under gravitational field, the space gets warped or gets curved, and if a particle tries to move in a straight line, but actually it ends up moving in a curved line, because gravitational field or gravitation has made the space itself curved. That is what is general theory of relativity. Again, these are all words. By listening to these things, you are not going to learn general theory of relativity. It requires several years of high level of training in physics and mathematics to learn that. But image you can make. Now, what happened to relevant to our story? What happened was that Einstein's equation in general relativity, um, automatically, by the equation itself, said that the universe must collapse because there was gravitation in it. Universe must collapse. It was a equation for the universe came out of general relativity, and the equation said that the universe must collapse. Now that was not palatable to Einstein. Einstein, this was 1915. Other galaxies were not known. All scientists knew, I mean, other galaxies were being discovered at that time, and we, by and large, the concept of universe at that time scientists had was that whatever we see in this galaxy, that is the universe, and that is static, more or practically static. Equation was saying, Einstein's equation was saying that it should collapse. Einstein said that what nonsense, So he just, in order to, there something must be, he just wanted a static universe, because a static universe was what was the dogma at that time. Everybody believed in static universe. Now, in order to make universe static, not collapsing, not expanding, he put a constant by hand in his equation, and that constant is known as cosmological constant. Greek capital letter lambda. That is the symbol he used for it, and it became famous. Cosmological constant is inverted V, the Greek letter lambda, and that, when he added that by hand artificially, he added that to his equation, and he stabilized the universe. Now, why did that stabilize the universe? If you add this some measure of this constant to Einstein's equation, it stabilizes, because, as I said, already indicated, that this cosmological constant in some way represents energy stored in the vacuum itself, in the empty space itself. So if only this cosmological constant was there, and no matter was there in the universe, the space will rapidly expand on its own. So this cosmological constant, this positive cosmological constant, you know, represents a property of empty space which can be seen as repulsive gravity. There is something repulsive inside empty space that makes it grow, larger. So the he deposited this property by hand in empty space, this property of expansion, which in some way counter the gravitational property of contraction, because gravity of matter is attractive. So that will make, gravity will try to make the universe collapse, and this cosmological constant, this energy stored in empty space itself, due to its repulsive gravity, will make the space expand. So expansion of a space somehow will compensate for the contraction of matter, and that is how Einstein created his static universe. Now, what happened was, this he was doing around somewhere 1917 or so, and 10-12 years later, in 1929, an astronomer, famous astronomer named Hubble, he discovered that actually, he discovered, first of all, galaxies. There was a very large telescope became operational. It is known as Mount Wilson Observatory, and he discovered, millions and millions of galaxies. So suddenly universe became very large. We thought that only the stars in our galaxy, in our own galaxy, that is what universe is. But Hubble discovers, Hubble and others, other names, I've always, the famous names are taken and many other names get buried in history, but many people worked, and they discovered uh, millions and millions of galaxies. But something very peculiar was discovered. All these galaxies, which were very far away from our galaxies, as I described in the beginning, they were running away from each other. And they were running away from each other according to a law. The law said that farther the galaxies, faster they are moving away from each other. So suppose we are in Milky Way, and we look at some galaxy which is 1 million light year away and is running away from us at certain speed, certain 1,000 kilometers per second, let us say, and there is a galaxy that is double the distance away from us, 2 million light years away. The galaxy which is 2 million light years away, running away from us at twice the speed of the galaxy which is at 1 million light years away from us. So double the distance, double the speed of running away. Now you imagine that situation. That universe is a large volume full of galaxies, and you locate yourself on any of the galaxy, and you look around on from any of the galaxy, what you will see that all the galaxies are running away from you, and farther the galaxy, faster it is running away from you. This is known as Hubble's law. So in a way, Hubble found out that the whole universe was expanding. So the universe is not static. And when Einstein came to know about this, he said that the cosmological constant was the biggest blunder of his life. He said that cosmological constant, my putting that constant into my equation by hand, is the biggest blunder of my life. Actually, we will see that it was not so much of a biggest blunder. This cosmological constant will not go away. It will be with us till the end of the story, and this cosmological constant is what is known as dark energy. But anyway, Einstein said that that was the biggest blunder of his life. Now, what happens you make a picture of the universe. If you extrapolate back in time, right now, if the universe is, as Hubble found out, if all the galaxies are running away from each other, you know, um, then if you extrapolate back in time, they must have been closer to each other in distant past. And there must have been a time when they would have been very close to each other. And because the gravitation is decelerating the expansion, gravitation is attractive, you know it is reducing the speed of them running away from each other. So in the beginning they must have run away from each other even faster. That was at that time that was the model. We will come to other complications with dark energy and dark matter later, but this, we are talking only of matter, because that time we imagined, in Hubble's time, we imagined that only matter is there, and only matter and ordinary energy, not dark energy. Ordinary energy is there, and the ordinary matter energy has gravitational attraction, so it will make the universe collapse. Something must have exploded with violent energy, so that with if you go back in time, the galaxies were running away from each other even at a faster rate, and gravitation will slow them down. So now we are seeing that they are running from each other, but in distant past they must be running away from each other at a much faster speed. And if you extrapolate back to zero time, you will have the image of a very large explosion. That was the universal explosion. The whole universe came out of that explosion. And later on, when galaxies were formed, I will come to that in a minute. When the later on galaxies were formed, they were running away from each other, driven by the force of the initial explosion and retarded by the force of gravitation. This was the picture that came out of the expanding universe at that time. Hubble calculated that it is possible, by looking at the rate of running away of galaxies, or rate of expansion of the universe. You can calculate back how many billion years ago the Big Bang would have happened. Hubble calculated it to be 1.5 billion years, which was very wrong, because there are rocks on Earth which are older than 1.5 billion years. The universe could not be younger than rocks on our own planet. That was because there were, the distances of galaxies and their speeds were being measured for the first time, and it is the difficult thing to measure these kind of distances. I can't go into the detail because of time constraint. So there were errors, and now those errors have been corrected to a large extent, and now the current value of age of universe is 13.8 billion years. The Big Bang happened 13.8 billion years ago. So this is and it was very hot, as I said. If you put all this matter and energy into a smaller and a smaller volume, it becomes hot. If it expands, it cools. If it contracts, it will become hot. So it would have been immensely hot at the time of Big Bang. The universe would have started in, you can't imagine what how hot, so hot that ordinary matter would not be possible. Atoms will not be possible. Even nuclei will not be possible. Even protons will not be possible. We will come to that. So initially there will be this soup of quarks and leptons, quarks and electrons, and so on. These are the fundamental particles as known today. Today we understand that there is nothing more fundamental than a quark or an electron. There are no subparticles inside an electron or inside a quark. So when it was extremely hot at the Big Bang time, we started, matter was in the form of a soup of quarks and electrons, and the particles that carry force between quarks and other particles, like photon in case of electrodynamics and gluons in case of quarks. Quarks interact with a particle called gluon as charges, electric charges interact with a particle called photon, the light particle. Anyway, you don't have to go into all those details. That is how the 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 universe was born in this hot Big Bang. And one relic of this expanding universe we see is the cosmic microwave background radiation. As I mentioned already, that this microwave radiation, which corresponds to 3 degree Kelvin, minus 270 degree centigrade liquid helium temperature, that radiation that fills the entire universe, where did that come from? And that in a way confirms this Big Bang model. What happened, and we will come to the history of matter a little later, but right now let me mention this as a proof of Big Bang, correctness of Big Bang model, that about 400,000 years after the Big Bang, more accurately 377,000 years after the Big Bang, the temperature of the universe became around 3000 degrees centigrade. And when it becomes 3000 degrees centigrade, it is cool enough for protons to capture electron. Till then, there are no atoms. Only protons and electrons are there. But it becomes cool enough for protons to capture electrons, and hydrogen atom is born. The first atoms are born. When were first atoms born? 377,000 years after the Big Bang. When electrons were captured by protons, radiation is emitted. That radiation was emitted all over the universe, and that radiation, which was very energetic. It is when an electron is captured by a proton. Um, uh, okay, let me just say a number. You don't have to worry about it. 13.6 electron volts. That much of energy is released, which corresponds to ultraviolet light. What was released as ultraviolet light 377,000 years after the Big Bang, now the same light, with the expansion of the universe several um, several thousand-fold, with the expansion of the universe, the wavelength of that ultraviolet light has become very long, and that ultraviolet light of that time that is what now appears as the cosmic microwave background radiation. So when it was discovered in 1965, it was discovered by two people who were not looking for it. They accidentally discovered it, Penzias and Wilson. There were other people who were looking for it, Robert Dickey, and a physicist, a astrophysicist and cosmologist, I think he was at Princeton maybe. He was looking for it. His team was looking for it, but they did not find it. Before them, Penzias and Wilson, two engineer kind of physicists who were experimenting with microwave radiation, building a large microwave antenna, you know, they accidentally discovered it in 1965, for which they won Nobel Prize in 1978. And this discovery of cosmic microwave background radiation, this was a proof that the Big Bang model, that the universe started in a very hot explosion of whatever matter and energy was there. And where did that come from? We will come towards the end of the talk. So whatever matter and energy was there, for some reason expanded in a massive universal violent explosion, and as the universe cooled, then atoms appeared. And when atoms appeared, they left a radiation. This matter and radiation decoupled from each other, became separate from each other, and then the universe became transparent. You could see, because then the light was became free to travel, without interacting with the atoms very strongly. Light was free to travel across the universe, which means that the universe became transparent. One could see through the universe. This, for the first 400,000 years of its life, universe was opaque. You couldn't see through it because matter and light all were strongly correlated. There was the light that could come to your eyes separating itself from matter, that was not possible. So now briefly, for a few minutes, let us talk about the history of matter. So what happened? Very early universe, the first picosecond, 10 to the power minus 12 seconds. Again, I should have told you that when I talk of very large numbers, I will also speak at times about very small numbers. 10 to the power minus 12 second means 1 divided by 10 to the power 12 seconds. You can't imagine how small that number is, and we will come to even smaller numbers, a little later. So the first picosecond after the Big Bang, I will leave that. That is known as very early universe, and I will talk a few minutes down the line. In early universe, the physics says, standard physics says that equal amount of matter and antimatter would have been created. If equal amount of matter and antimatter would have been created in that Big Bang, then we would not be here, because matter and antimatter annihilate each other, and only radiation will be there in the universe after all the antimatter is annihilated by all the antimatter, which must be equal in number or equal in amount, according to the basic physics laws. For some reason there is little bit of excess of matter compared to antimatter. We don't understand, physicists don't understand it very well. There are guesses about it, that somehow there is something called CP violation. There are some symmetries in nature. you know if they are little bit violated, they will give rise to little bit of excess of matter compared to antimatter. So mostly matter will be annihilated by antimatter, resulting in radiation, but little bit of matter will be left over, and that little bit of matter will give rise to all of us, all the galaxies, all the clusters and superclusters, all the stars, and whichever star has a planet, and whichever planet has life, all that will come out of that little bit of excess matter, that matter antimatter disbalance, or matter antimatter asymmetry, as it is known, and that is responsible for all that we see in the universe. Now, um, when the universe was roughly about 1 billion degree centigrade, that hot, let's say, I mean, less than a second, after much less than a second after the Big Bang, then quarks came together to form protons, and between 2 minutes after the Big Bang and roughly 20 minutes after the Big Bang, something called nucleosynthesis happened. Protons came together, and neutrons also, some neutrons also came about, and and protons, you know, are hydrogen nuclei. The nucleus of hydrogen atom is proton. That is the simplest, lightest atom that you have. um, for a physicist, easiest atom or most familiar atom, you know, hydrogen atom. Now, had hydrogen atom's nucleus, protons were formed um, um, when universe was a billion degree centigrade or so, and between 2 minutes and 20 minutes after the Big Bang, these protons came together and they formed heavier nuclei like deuterium, which was soon turned into helium. And another success of Big Bang theory is that once in 20th century we came to know about nuclear physics, we came to know about nuclear forces, and we came to know about nuclear reactions. We could calculate that between 2 minutes and 20 minutes after the Big Bang, if this was the temperature suitable for formation of helium nuclei, then during that period, how what proportion of protons will be converted into helium nuclei. And the calculation says that we should have in the universe 75% hydrogen and 25% helium. The calculation says that, and that is what we observe. The universe, the ordinary matter in the universe is mostly hydrogen and helium. Heavier elements are minuscule, very little, you know, and they are cooked in stars and supernova. You know, we will mention that a little later. But most of all of universe is 75% hydrogen and 25% helium, and this was a prediction from nuclear theory and from the Big Bang model, and the prediction was right on dot. This was a prediction of Big Bang model plus nuclear theory, and it came out right. Again, one more evidence that the Big Bang origin of universe, that theory or that model is correct. And then 377,000 years later, another big event happened that I have already described, that these protons captured electron and hydrogen atom was born, you know, and same way helium nuclei would have captured two electrons and helium atom would have been born, you know. So atoms were born 377,000 years after the Big Bang, and then neutral matter, uncharged matter, which is in the form of atom, that we see only after after this what is called recombination. It was the first time it was being combined. Recombination we say because of habit of certain habits of physicists. Recombination means nuclei captured electrons and turned into atoms. So that combination of nucleus and electron forming an atom, that happened 377,000 years after the Big Bang, and that is when neutral matter, neutral atoms, that is what most of universe is made up of, you know, that came about. And that is why, because all the matter in the universe is neutral, that is why at long distances you don't see any other force. You don't see nuclear force, which does not work at long distances anyway, and electromagnetic force, which can work long distances, is not effective, is does not work in the universe at large, because all the matter in the universe is uncharged. So no electric force drives the dynamics of the universe. So which is the force that is left to drive the dynamics, the motion of the entire universe? Gravitation. When it comes to universe, gravitation is the only force that is determining the dynamics of all these large clumps of matter, which are known as stars and galaxies and clusters of galaxies. Now, I should quickly mention two more discoveries, and then we will be moving towards the end of our story. Those two big discoveries were the discoveries of dark matter and dark energy. Dark matter, the discovery happened in 1970s when certain astronomers were measuring the rotation of galaxies. One very famous astronomer, a woman astronomer, Vera Rubin, she was the pioneer. She measured the rotation rate of galaxies, and it was calculated that the rate at which galaxies are rotating and the ordinary matter that is there in the galaxies should not form. The speed of rotation is so large compared to the gravitational attraction of all the ordinary matter that is there in the galaxy, that galaxy should scatter. The stars should be scattered around. You know, if you move something, a stone, um, tie it to a rope and rotate it very fast, in your hand, you will feel a force on your hand, what is known as, centrifugal force. It is a fictitious force, centrifugal. Actually the force is inward, but you feel the force that the stone is trying to run away from you. The galaxies were running at such a fast rate that all the stars should have run away from the gravitational pull of each other. Galaxies would not be formed. This was a major, major mystery. And it was not a little bit of effect. The galaxies should not have been there at all, if they were formed by gravitational attraction between the stars that formed that galaxy. So it was then calculated that the galaxies have lot more mass inside them than is visible in the form of stars. And it was not a small number. In fact, whatever matter was visible in the galaxies, 5 or 6 times more matter was contained in those galaxies. The galaxy rotation that gave how much mass was there inside those galaxies, and that is what it gave rise to, I mean, gave us the indication of presence of dark matter. There is some kind of matter all scattered all over the universe, and more so in the galaxies, because gravitational the dark matter is such that gravitation acts on it. It has Dark matter also has gravitational attraction, the same way any energy or any matter has, but it doesn't have other interactions. So it is not ordinary matter. It does not emit any light. It doesn't have nuclear reactions. No. So it is altogether different from ordinary matter that we know. But it is matter in the sense that it is influenced by gravitational force. So the total matter, dark matter, plus ordinary matter, then you could account for why did stars come together in the form of a galaxy. Why were galaxies born? Without dark matter, you cannot have galaxies. And if you don't have galaxies, the way the universe looks, the way the universe is, that does not get explained. So that was one. This is why I said in the beginning itself that 25% of all energy and matter, all content of the universe in energy terms, 25% is dark matter and 5% is ordinary matter. So you see, dark matter is 5 times more in weight or 5 times more in amount, than ordinary matter. This was discovered when galactic rotation was measured, and it was calculated that how much matter is inside the galaxy. Those rotation indicates that, those rotation gives a handle on that. The second big discovery was even later than that. It was in 1998. We discovered, the physicists discovered, and they got Nobel Prize for that. Vera even did not get Nobel Prize for that. I think she should, but I don't know whether, I mean, she is around or not. Um, mm, but the people who made this discovery in 1998, it was a stunning discovery. It was a stunning discovery. The discovery was that 5 billion years ago, uh, the universe started accelerating. So you remember, universe started in a big explosion. Gravitation was retarding it, decelerating it, is reducing the speed of galaxies which were running away from each other. But about 7 or 8 billion years after the Big Bang, or about 5 billion years ago from now, the universe suddenly started speeding up. as if, when you are driving a car, suddenly you put your foot on the gas, on the accelerator, it started accelerating. This was a stunning discovery, you know and this is now well established. you know Many other measurements have been made, after that. And this sudden acceleration of entire universe that happened 7 or 8 billion years after the big bang, how could you explain that? How There is only one way to explain, and that is Einstein's cosmological constant. Einstein's cosmological constant, which means that a space by itself has something, vacuum has something inside it that makes it expand, that makes it grow on its own and grow at a very fast rate. So this is the something stored in the empty space itself, and that is what is known as dark energy. So Einstein's cosmological constant is same as dark energy. Dark energy is what is represented in the equation as Einstein's cosmological constant. So in a way you can say that 1998 discovery, sudden acceleration of universe, proves that what we thought, that only matter is there and the space by itself doesn't do anything, and for some mysterious reason initial explosion was there, because of which the galaxies were running away from each other, and all gravitation was doing was decelerating them. And depending on how much matter is there inside the universe, the gravitation will be able to pull them back together if there is enough matter, or if there is not enough matter, then the initial explosion will win over, and the universe will escape into, escape away from each other's gravitation. The galaxies will escape away from each other's gravitation. So that will be open universe. So open universe is something that will not return. Gravitation will not be able to make it recollapse, and closed universe is that gravitation will finally win. There is enough matter in the universe for gravitation to bring all the matter together. So there will be a big, as there was a big bang in the beginning, there will be a big crunch again in the end, when all the matter will return to a point, will crash against each other. That was, and so how much matter do you need in order to have an open universe or a closed universe? Or there is this perfect equilibrium where the universe does not come back but does not go into oblivion either. It, the expansion slows down, and it slows down at a rate that the expansion will go on forever. That is known as flat universe. That flat universe requires a critical mass energy density. So if the universe has that critical mass energy density, then there will be flat universe. Before this discovery of 1998, we thought that it is more or less balanced. We live in a flat universe. We live in a flat universe because otherwise universe would not have survived for 13.7 billion years. The fact that it has survived for so long, so many billion years, it is almost exactly flat. It is almost exactly that gravitational pull and the initial big bangs uh, push out, they will balance each other, and the universe will go on forever, never go into oblivion completely, or never collapse back. That is the model we had until we got this shock of 1998 that universe is accelerating. And how could you explain that? There is only one way to explain that: there is a little bit of dark energy, and when the dark energy density is small, and when the universe is very small, close to the Big Bang time, or a billion, 2 billion, or 5 billion years after the Big Bang time, the universe is small, so the matter energy density is large. And if matter and energy density is large, then gravitation is large. Then gravitational attraction overcomes this dark energy effect. The dark energy effect is always there. The dark energy effect is the effect of the vacuum, effect of the empty space. So empty space on its own is always expanding. But in the beginning, universe was a small and matter and energy density was so large that gravitational pull overcame the expansion property of expansion of empty space. The dark energy was overcome by the gravitational pull of ordinary matter and energy. So initially, after the Big Bang, the galaxies were decelerating. Their running away from each other was slowing down. But as the universe was expanding, the density of matter and energy was becoming less and less. And there came a point that when the density of energy and matter became small enough so that the gravitational pull of energy and matter became small enough, the dark energy finally had its day. Dark energy, the effect of dark energy became larger than the effect of gravitational pull. The point at which the effect of dark energy will become larger than the gravitational pull of matter and energy. That is the point at which the universe will begin accelerating, because now the dark energy is in the driving seat. Dark energy is the effect of dark energy, which is expansion, which is accelerated expansion, that will overcome the gravitational pull. And that is what was discovered in 1998. So before the acceleration, we call there was the matter and energy dominated era of the universe, and now we are living in the dark energy dominated era of the universe. There was a turning point. There was a turning point 5 billion years ago, when dark energy became a larger effect than the gravitational pull of ordinary matter and energy. So this completes the picture of the universe, except that the origin question is still not answered. Why did the Big Bang happen? We are just saying that something made the whole universe explode, and whatever energy, was there in that explosion, that is making the galaxies fly away from each other, and gravitation is trying to pull them back, and dark energy is trying to push them away, you know and that tussle, that tug of war between dark energy and gravitational attraction has been taking place. That has been the history of universe. But what was the initial explosion? Where did that come from? In fact, you can ask that, where did all this matter and energy come from? Now that was a question that was not answered in the ordinary Big Bang theory. In the standard model of Big Bang theory, it was just assumed that for some reason Big Bang happened. But there were other problems with that Big Bang theory. The one problem was that I talked about, that we live in a flat universe. But if we live in a flat universe, the universe should have been so flat, the mass energy density should have been so exactly critical mass energy density, that if you deviated from it even one part in 10 to the power 50, I mean, that's an unimaginable number, you know 1 followed by 50 zeros, one part in 10 to the power 50, if you deviated that much from the critical mass energy density, you will not see the universe today. Because if it was mass energy density was little bit less than that critical mass, that little less, 1 in 10 to the power 50, that much less than the critical density, then the universe would have run away, and nothing will be visible. The universe will be completely dark, and there will be no time for stars to come together, galaxies to be formed, and obviously we will not be around to see and talk about these things. That hasn't happened. And if the mass was 1 in 10 to the power 50 more than the critical density, then the universe would have collapsed long ago, and again there would not be enough time for galaxies to form. It would have gone to the big crunch, it would have recollapsed, universe would have recollapsed. So how was this fine tuning done? How come you can have a big bang, such a massive universe, big bang, a universe coming out of big bang, and so fine tuned that it is fine tuned in one part in 10 to the power 50 or 60 or 10 to the power 100, so that universe is Even today, 10 to the power 13.7 billion years after the Big Bang, still it is flat. It is flat universe. It is not collapsing, or it is not running away into oblivion, so that nothing is visible. The sky becomes dark. You know, still we see stars and galaxies in the sky. So that was a big puzzle for Big Bang. And the other big puzzle was what I have already talked about, that no matter which direction you look around, the universe is same. The microwave radiation, background microwave radiation, for example, it is same all over the universe, no matter which direction you see and no matter how far you see. It's the radiation density or energy density of the microwave radiation is the same. So you see that the large scale universe is homogeneous and isotropic. Now the problem with that is that when this microwave radiation was created as an ultraviolet radiation 377,000 years after the Big Bang, at that time not all the parts of the universe were in touch with each other. And if not all parts of universe were in touch with each other, in touch with each other means affecting each other, then how did they thermalize? How did this uniform temperature got established? You know that in order to, if you put very hot water into cold water, an average temperature and a median temperature is established, but for that the entire hot water has to be in touch with the entire cold water. That is what is called thermalization. And this kind of thermalization, that we see this large universe thermalized at one uniform temperature, how did that happen? Because the time at which this radiation was created, 377,000 years after the Big Bang, at that time every part of the universe was not in touch with each other, and it was expanding so fast that it was never going to come in touch with each other. So this is known as the horizon problem, that different parts of the universe were never in touch with each other. So how come they all established equal temperature, equal energy density, this homogeneity and this isotropy? And there were other problems too, but these were two major problems of the Big Bang theory. So the way this problem was solved is something called a model called inflationary universe model. It was a model that came out in 1980. That was the time when I was doing my PhD, and I heard this story from the person who who came up with this model. His name is Alan Guth, and I was doing my PhD at MIT, and that is where I heard his talk, and that is where he had 6 years earlier done his PhD. And when he came up with the spectacular inflationary universe model, then he was not getting a job anywhere, and suddenly everybody was giving him a job, and he accepted the job at MIT. Now he is a famous professor at MIT, where of course, I mean, it's not self advertisement. That is the alma mater. That is where I did my PhD. Anyway, so what was this inflationary model? Inflationary model is is a revolutionary kind of idea in many ways. It's revolutionary in the sense that it joins largest scale physics with the smallest scale physics. The smallest scale physics is particle physics. Largest scale physics is cosmology, what we have been talking till now, the origin of universe and so on. Now, smallest scale physics, particle physics, talks about needs quantum theory and needs field theory. There are four forces in nature, and so on: the gravitation, electromagnetism, and the two nuclear forces. And one of the nuclear forces and electromagnetism has been unified by a famous physicist, Abdus Salam and Steven Weinberg. It is called Weinberg-Salam theory. They unified into one force. So they showed that electromagnetism and weak nuclear force are the same force at very high energies. Only at low energies where we live, they become separate forces. And there are speculations that if you go to higher energy, the strong nuclear force will also become unified with the electroweak force. The Weinberg-Salam unified theory is called theory of electroweak force. So this grand unification, you know, those were being talked about in those times, 1970s and 80s, you know. And what happens in these unification theories, in these quantum theories of unification of forces, is that the again, these are technical things. I cannot go into detail, for not only for time constraint, because also because I am myself not an expert of it, you know, and whatever little I know, I cannot tell you without getting into technical physics, you know. So, but one thing, let me say that the ground state of a quantum field theory is the theory of these fundamental forces. So the ground state of a quantum field theory is the theory of these forces and these particles. So quarks and electrons and these electromagnetism and nuclear forces, all these forces and all these particles, that is what constitutes particle physics. And the fundamental theory is known as quantum field theory. The quantum field theory that describes all the fundamental particles and their three forces, electromagnetism and the two nuclear forces, is known as a standard model of particle physics. The standard model of particle physics, you know, when you have these unification strategies, then you see that the ground state of a quantum field theory is called vacuum. Vacuum is the ground state when no particle is there, you know. But quantum theory says that this vacuum, this nothingness, this empty space is not actually, you know, complete nothingness. There is a lot of activity there, and quantum theory allows those activities. Quantum theory allows that in the vacuum, in the nothingness, particle antiparticle pairs will arise for a very short time, and then they will annihilate each other, then they will disappear. So these are called virtual particles. These virtual particles will appear and disappear, and on the average there will be no energy in the vacuum. That is why the energy of the vacuum is zero. That is why it is zero. But if you look at very close distance, very small distances, then if you had that kind of microscope, we don't have, but if you had that kind of microscope, you could see the vacuum seething with these virtual particles coming into existence and disappearing. So vacuum is not really, according to quantum field theory, that vacuum. It has some medium kind of, it behaves as if it is some kind of medium. So, and if it is some kind of medium, the quantum field theory people also discovered that there are phases of this vacuum. The vacuum of the quantum field theory of the standard model, there are phases of their vacuum. There are higher vacuums at very high energies, and there are lower vacuums. You know, now we assume that the lower vacuum has exactly zero energy, and compared to the lower vacuum, the higher vacuum had much more energy. It's like two phases of matter. It's like ice and water. Ice and water are the same things, but ice can melt into water, you know. Same way, the vacuum had phases. Vacuum of these quantum field theories had phases, and the higher vacuum, for some reason, it is known as false vacuum because it decays into the lower vacuum eventually at lower energies. So the higher vacuum, the higher energy vacuum, is known as false vacuum. Now false vacuum, in comparison with the real vacuum in which we live, in comparison with our real vacuum, the false vacuum, depending on which theory you are talking about, which unified theory you are talking about, it has tremendously high energy density. Now, if a vacuum has tremendously high energy density, remember that is the dark energy. Dark energy is nothing but the energy of the vacuum. And if there is tremendous dark energy in some vacuum, Einstein's general theory says that it will explode. It will expand so fast because of the repulsive gravity that is there in this false vacuum, which is highly energetic compared to the real vacuum. It will explode. It will grow very fast. You cannot imagine how fast, but it will grow very fast. Now if you get a droplet, a small droplet of the false vacuum, within no time that a small droplet of the false vacuum will grow very large. And if that small droplet within no time grows very large, remember that is still the false vacuum. False vacuum means every cubic centimeter has that energy density, the very high energy density of the false vacuum. So somehow the repulsive gravity of the vacuum operates in a way that the vacuum expands, this small droplet of false vacuum expands, and as it expands, because it is vacuum, because the energy density is constant and volume grows, the energy of that vacuum grows. The total energy density remains constant and volume grows, which means the total energy grows. So this was, a very, strange. It's very difficult to come to terms with, those of us who are accustomed to, regular physics and regular energy balance and conservation of energy and so on. I cannot go into those technical details. I am already end of my time. So this grows very fast, and when it grows very fast, at some point it decays into the real vacuum. you know so the false vacuum grows very large and decays into the lower vacuum. So all the energy that is there in the vacuum, in the false vacuum, become available for creation of matter and energy, for creation of ordinary matter and ordinary energy. That is how ordinary matter and ordinary energy was created in the beginning of the universe. That is the beginning of the history of matter and energy. It came from energy stored in the false vacuum. And where did that original droplet of false vacuum came about? We don't know. The answer is we don't know the answer to that, but we always go to unknown physics, starting from known physics, starting from known facts, and the only way we can explain the Big Bang is through, right now, the most believable model is this inflationary model that starts with a droplet of false vacuum, which grows exponentially fast, decays into normal vacuum. The energy difference is available for creation of matter and energy. It is when all that energy turns into matter in a very small volume compared to today's volume of the universe, it is very hot, and then after that, whatever story I have already told you, the standard Big Bang model story, that takes over. So the beginning was done by inflation of the false vacuum, the large growth of the false vacuum that started at 10 to the power minus 35 seconds after the Big Bang, and and stopped at somewhere 10 to the power minus 32 seconds after the Big Bang. You cannot imagine how small durations of time, but that expansion was so fast, that the universe grew in that between 10 to the power minus 35 and 10 to the power minus 32 seconds. Universe grew by 10 to the power more than 10 to the power 25 times. It grew larger, and so that energy became available for creation of matter and energy in the universe. That is the story we have so far. We still don't know why there is little bit of dark energy in our normal vacuum, because we discovered that in 1998, that our normal vacuum, we assumed that the false vacuum has energy density, but normal vacuum has zero energy density. But in 1998 we discovered that that is not true. There is a very small energy density in the normal vacuum too, and this normal vacuum is also expanding on its own. We have discovered that. That is what is known as now existing dark energy. Now existing dark energy of the normal vacuum, is what is 70% of the energy content of the universe. Now, why we have this small amount of energy density, small compared to the energy density of the false vacuum in the beginning? Now remember, universe has accelerated twice. Once violently, that was in the inflationary universe. That was the expansion of the false vacuum, and then it accelerated again, slightly accelerated again 5 billion years ago. That is the acceleration when the dark energy of our normal vacuum started going ahead of gravitational attraction. So universe in its whole history has accelerated twice. Now, first acceleration we understand was because of the false vacuum, and particle physics one day aims to explain that. Particle physics come up with the complete answer why, where did that false vacuum come from. But why does our normal vacuum still has a little bit of dark energy? We do not know. And probably that will require knowing that where does this come, a complete theory of all the forces, complete quantum theory of all the forces, which includes quantum theory of gravitation, which we don't have. So those are the details we cannot go into. To conclude, I will say that this is the story of the origin of universe, and this is the history of how matter was created and how it clumped and how galaxies were formed. I have not talked about how solar system was formed and how planets were formed and how life was formed. I haven't come to that. That's a very long story, but another story. So this is the history of matter that I have given you, and what we still don't know. We don't know that where did that false initial droplet of false vacuum come from. We don't know why does the normal vacuum, today's vacuum, has little bit of dark energy, and what is that. We don't know what is dark matter. Dark matter is definitely there. Without that, galaxies will not be formed. But we don't know what that dark matter is. That is very different from ordinary matter that we know about. And we don't know why there is little bit of matter antimatter asymmetry, why matter is little bit more than antimatter, so that we are around, so that normal matter is around, so that galaxies are around. So in a layperson's version, this is the full story, and I will stop here. Thank you.